We're going to be making this ISO grid or triangular tiling. This is what the node setup for the finished shader looks like. This is just the ISO grid, and then this is to make it look like this, you know, bump mapping, principled shader, basic. So I'm going to be showing some things here in Krita, and then here as well. This is a really nice website, the Book of Shaders. And so here they have some interactive WebGL or GLSL, and that way you can see how you could make this ISO grid. So the idea here is based actually on how they make simplex noise. And so might be best if I just show you. So this is the standard 2D grid using Fract, and then we can scale it to make it skew, so like that. And the exact factor that we need to scale we'll look at later. And then once it's skew like this, you can see that each of these rhombi, I don't know, a rhombus, if you divide them into two, then you get two isosceles triangles, and that way we can create our ISO grid. And that's exactly what you do here. And the three colors here, the red, green, and blue, just give the distance from each point. So the distance from each vertex of the triangle, and that in the X, Y, and Z, or RGB. So that's what we'll be doing, creating this. In addition to that, we'll also create a shader which shows the index of each triangle, which you can then use to assign random seeds to each of the triangles, just like we had with the hexagon node. Alright, so let's go to Krita first. So yeah, as it says here, a simplex grid of triangles can be skewed by a non-uniform scaling, blah blah blah. It's not really that important. What's important here is if we compare the x and y value, if y is greater than x, then we're in the top triangle, and if x is greater than y, then we're in the bottom triangle. We'll use that later to create a factor. So this is like what the ISO grid would look like. And how we're going to make it is such that the height, or well, the side length of each of the triangles is going to be exactly 1, and that means the height has to be the square root of 3 divided by 2, which you can find using trigonometry if you know that this angle is 30 degrees and this is 60, because it's not an isosceles triangle, an equilateral triangle. That's what I've been trying to. Then you know that the sine of 60 degrees is square root of 3 divided by 2. Yeah, so then when you scale by square root of 3 divided by 2, then you get a problem because your boxes or your grid becomes actually the inverse of that. So like if you scale by 10, then each of these has a length of 1/10. So we actually, if you want them to have a length of 10, we need to scale by 1/10. So that's why we invert it, and that's 2 divided by the square root of 3, which is approximately equal to 1.1547. So now we can actually go into Blender. Let's see. So I've prepared right here. So we're just using Eevee. Let's go to top view. And the first thing we need to do is to create our grid. So just like here, create our grid using the fractal and then multiplying everything by 10, for example. So let's add in a vector map, and then we set it to scale. And because I know we're going to need this later, I'm going to make the scale a value like that, and then let's set it to 10. So now we have the values going from 0 to 10. And the next thing we need to do is take the fract. Well, normally that's what we would do. in this case, since we're first going to skew it, we're only going to take the fractional part later. So let's go and add a separate XYZ, because we need to scale the X and Y components differently. So we need a vector math node. Then we'll set this to multiply. And now we need the square root 2 divided by the square root of 3, which is 1.1547, and then 2 zeros and some other value. But since we're only working in floating point, we don't need that much precision, since it's going to be get lost anyway. And now this scales it along the x-axis. And now we could, for example, take the, where is it, floor right here, and then you can see that we get different values. And if I copy this and change it to a subtract, and plug this into the bottom value and this into the top, and this just gives our fraction. And the reason I'm separating it out like this and not just using the fraction node is because we'll need the floor component later anyway. That way we save some nodes. So let's move this back a bit more. And now for the Y part, if you just take the Y component now and subtract it, then we get this. But we actually want to move it down, because here it's right straight, but then here we push it down, and how far we push it down depends on the x value. And so right here, so here we scale it by 2 divided by the square root of 3, and here we need to scale it by 1 divided by the square root of 3 times the x value. So what I'm going to do is I'm going to use the multiply add, and I'm going to multiply this x value by 0.5 and then add it to the y, and that way we can see that we've moved it down. So if we were to combine these using a converter, combine XYZ like that, then you can see that we get this, which is exactly the same as this one. The colors look a bit different because of the color management. I'm pretty sure if I set it to standard, it will look similar, and because there's lighting and so on. So let's just set this back to filmic. But we don't want just a squashed square grid, we want triangles. So now we're going to take advantage of this simple fact that if the y value is greater than the x value, we're in the top, and if the x value is greater than the y value, we're in the bottom. So we can just do a compare using a math node, set this to greater than, so y is greater than x, and now you can see we get all the triangles. And we don't want this, so we're going to use the combine XYZ later. So this is our factor basically, checking if x is greater than y. And now we need the distance from the edge, so I'm going to duplicate this, and then in the end I'm going to add a color mix RGB, and so we can plug this into the factor. And so this is for the case that we're in the top half, and this is in the bottom triangle, right? or maybe it's the other way around. Let's see. So x is greater than y. Then we're in the bottom part. So if this is true, then we go. So this is the bottom and this is the top, which is a bit confusing. So let's change it to less than. So let's go back to the website. Here it says for if x is greater than y, then we do this. So the z should be just our y component. So this is, remember, this is less than, so this will be the bottom one if it's greater than. So this is our y, where we just plug it into the z. So this gives us our distance from this point, which makes sense, obviously. And then for the other one, this is going to be 1 minus y, right? So for the other one, you're going to see 1 minus y somewhere right here for the z component. So let's do that as well. A converter math node, subtract 1 minus y, like that. We plug this into this z value. So now we've taken care of the one of the points. So now we need to take care of the other points. And for that, we're also going to need the x value and 1 minus the x value. So let's duplicate this. And maybe let's move this closer to here. And this to the bottom. I'm not really that great at arranging nodes. So, right, so let's do 1 minus the x value. And let's think about this. So the distance to this point, well, that's the most difficult one, I think. So the distance from this point is just 1 minus the x value. So let's see what so here 1 minus the x value, they put it in the x component. So let's do that as well. Let's unplug this to see which one. So yeah, we're in the wrong. Let's plug it into this one. And for the other one, it is just the x component, as you can see here. So now we still need the distance from this point, which is going to be our y. So this is our x. No, this is our y. This is our z. This is our x, and this is our y. And now for the y, we need to combine the x and y values together. So if x is less than, then we need to do 1 minus the x component and then add the y component. Sorry for that. So now what this gives us is the distance from this point, well, in x and y. It sort of gives us a smooth blending between, so the influence here of this point is the strongest, and then here is this, and then once you get to the center, it becomes a clear mix between the two. That's why you get a wide value. So what we can do is instead of putting the centers in the 3 corners, we can put all the 3 centers at the center. So let's add in a vector math node and then set it to subtract. And then the center is just, we can just do 0.0. So we can just do 2 divided by 3. Like that. So you can see I did the same thing over here. And the reason that I prefer it like that is because now if we, for example, add in a separate XYZ, and we just look at the X values, and we can use this as a sort of distance from the center of the triangle in the X direction and the Y direction and the Z direction. It's not really X, Y, and Z, but really the 3 sides of the triangle. So now if I do, for example, duplicate this one and set it to a dot product with itself, you can see it gives us the distance from the center of the triangle and looks like Voronoi sort of stuff. It's not really Voronoi. So that's one thing we can do. Then the other thing we could just do is, instead of doing that, we can use our separate XYZ, and then we can add in a math node and take the maximum. So let's use smooth maximum so we can change the values later. Sorry, let's use the Y and duplicate it. Now we use the Z. As you can see, this gives us sort of distance to the edge, and it's this one that I used to create the pattern you saw. So for example, you could add a color ramp, change the first one to red, and change this one to black. Something like, it's not really red, change it to be a bit more red. Something like that. There you go. So that's what I did there, and then I also used this as the height value for a bump map to get the sort of reflections. But now the other thing we can do is try and get an index for each of the triangles. So to do that, we already have the floor here, right? So let's add in another combined XYZ. And this is going to be, so for the Y value, so if you just plug the Y and the X into here, let's bring this down like that. Then we get something like this. This is just the, again, the square grid. So we need to use this factor somehow. So what we can do is add in a math node and set it to multiply add. Then we can take this and multiply it by 0.5. And now we get a factor. Maybe I should get this greater than. Okay, so. And then switch these two. So now we have a unique index for each triangle, but if you want this to be in a square pattern and not slanted like it is now, we need to add back some of the Y value. So to the Y, we add the x value multiplied by minus 0.5, like that. So then in the end we could still divide by our scale to bring it back in the 0 to 1 range. And let's do that. So let's add in a math divide. So let's connect this to the divide and then bring it down like that. So now we can do the same thing with our x values. Something like that. Or this is our y value rather. But the problem is this is not yet completely correct, because we scaled along the x-axis here by 1.15, so that's why we still need to duplicate this and then change this to divide. So now this is also in the 0 to 1 range, and you can see if I increase the scale, then it starts to look just like our normal UV, right? So like that. Set this to 1, or no, something like 10. So another interesting thing that we can do now that we have this, so you could make this into a node group, obviously. Instead of taking the maximum, right, we could change this to be minimum and just look at that. Now the problem is these values are negative, so to change that we need to add a value, and this is going to be square root of 2 divided by 2. And now you can see we get hexagons, and really what is happening is, so previously we got this is the center of the triangle, and we were using we're getting the distance from the center to the edges or to the vertices, and now what we're doing is we're inverting it sort of, and we're getting the distance from this to, and that's why each triangle gets like this pattern right here. But then if you line them up like in this grid, it's going to create hexagons, which makes it look like it's hexagons. So let's just change these back to smooth maximum, and then you could plug a value into here to change how sharp it should look, right? Depending on your preference, of course. Oops. Something like that. Pretty cool. And then what you can do is add in a vector bump, and then a shader, principled shader, and plug this to the normal, plug this into the height. Now this is obviously insane. So let's set the distance to something like 0.2. It's also too much. 0.05. Still too much. 0.02. Now you can barely see anything. 0.1. Yeah, something like that. Still a bit too much, but so now you get the idea. and then you could obviously change these to smooth minimum. I can do that right now. And then play around with this value. And let's plug this into here. So yeah, that's the creative part. You can think of what you want to do. So this is the ISO grid, and the one problem with this, well, it's not really an ISO grid. It's a grid of equilateral triangles. It's a triangle grid. So the problem with this is if you do something like a cube, right? And then we give it this material. The light, let's scale it down because it's blocking the light. You can see that some of the edges, like right here, don't blend well. That's because it's a 2D texture and we're using the UV. So if you don't have good UVs, then the seams are going to be obvious. So I'm still trying to find out if there's a way to generalize it to 3D, because currently what I've found so far isn't really a way to. This is not how you should generalize it. I'm trying to follow also the simplex, because simplex can be generalized to n dimensions, and then you get a squashed tetrahedron, but it gives weird results, as you can see, but it's not really it only works on one side at a time, right? So I'm still looking for a way to combine it correctly to get the same effect, but then in a 3D texture. So yeah, that's the video. I hope you guys liked it. And if you have any questions, you can always leave a comment. So yeah.